We're going to look at some key results in likelihood theory that we'd like to use with the exponential family. And if we just state the two results are that the expected value of the score equation is equal to 0, and the expected value of minus the information is equal to the expected value of the score squared. Quite how we use this won't be at all clear here, but if we're going to state results like this, it would be good just to check them. Now, let's just check a couple of ideas. So we have some density function or a mass function which can become a likelihood function if we make it a function of theta given y, but there's a specification of the two functions are identical. And we can also take logs of these things to form a log likelihood function. And on this screen we're going to run out of space very quickly if we don't shorten the notation. So if we denote a log likelihood by a script L, and we'll denote a density function by a lowercase f, and then slightly better notation, the dl of theta with respect to theta, the differential of the log likelihood with respect to theta, which we may, depending on space, abbreviate to d of l with respect to theta. This is what's called the score equation, s of theta. And then if we take the second differential of the log likelihood, and again we might abbreviate that to just the L, depending on space. This is what's known as the information. If we evaluate that at the maximum likelihood values, we have the observed information. So we're going to look at some results based around these, essentially to find the expected values. Now, one calculus we're going to use quite a lot is that if I take the differential of the log of a likelihood function, I'll write this slightly shorthand in a moment, but if I take the differential of this log likelihood, it's equal to 1 over the density function multiplied by the differential of that function. Now, again, because we're going to run out of space, we'll actually write that out as d of L d theta is equal to 1 over f df d theta. But when we use this shorthand notation, that's what we're referring to. The log of a function with respect to theta, 1 over the function df d theta. And we're going to use that a couple of times in working this through. And essentially what we're going to do is to take expectations of this, and if we look at both sides of this, we can see exactly how this all hangs together. So what we need to do, we have the score equation dl d theta, we have another way of expressing the score equation, and we want to find the expectation. So expectation is all about finding the integral of some function of a random variable multiplied by its density integrated over the range that applies. So if I want to find the expected value of S, I'm trying to find the expected value of dl d theta. So I need to find the integral of dl d theta with respect to the density function that applies over y. And that, of course, expressed in a different way, the integral over y of 1 over f df d theta, and I have an f because I'm applying that density function. The fun starts here because we're going to apply a procedure that's usually, I think, okay with maximum likelihood problems, but not generally and automatically a safe thing to do. But we're going to reverse the order of these operators. We're going to move the integration sign inside, and we're going to move the differentiation sign outside. You can see instantly on the right hand side here some tidying can go on. I have a 1 over f multiplied by an f. So when I do my rearranging, if it is indeed valid, I have d theta of the integral over y of f with respect to dy. And of course, because this is a valid probability density function integrated over its entire range, we automatically know exactly what value the integral of f dy takes. That's equal to 1. So I'm left trying to find d theta of 1, which is equal to 0. So I have the result that the expected value of the score is equal to 0. Okay, so if that's the score sorted, the next one we want is the information. So if I move this to one side, the idea we're going to use here will involve us taking the second differential of the likelihood, and we're going to use the identity that that's the second differential of the density function minus the first differential squared. So this is the identity that we're going to use, and all we really need to do here is to take expectations, and if we just use the expectation of d2l d theta is equal to the expectation of all of these terms here, and of course we know we can break these terms up if it's an expectation, so we have the expectation of second differential of f theta 1 over f minus the expectation of df d theta 1 over f all squared. And although the print is getting rather small, we should recognise this term here, which is the same as the terms we're working with here. So this is in fact minus the expectation of the score squared. And this term here is the expectation of what we're calling the information. So if we can show that this term here is equal to 0, we've found an expression, the solution that we wanted. So let's look at that term. What we have, we're interested in the expectation of the second differential, should have had a 2 in there, 1 over f, and of course this is the integral of the second differential of the density function multiplied by 1 over f, and we're taking an expectation, we need to multiply that by the PDF and take the integration with respect to dy. So we've seen all the tricks we need to know. These cancel, and we're going to reverse the order of these operators. So what we need to do is to find the second differential of the integral of f dy, and of course that is equal to 0. So by finding that result, we've solved the original problem, and to say that the expected value of the score is equal to 0, and that the expected value of minus the information is equal to the expected value of the score squared. These two results, very useful, crop up everywhere. These are specifically interested and give us a couple of great properties for the exponential family distribution.